So, hello everyone, this is David Taylor, and this is my contribution to the mini symposium on applications of the TCD. It's a new experience for me recording my talk like this, as I'm sure it is for many of you, so hopefully this will go okay and you'll be able to hear everything. So, big thank you to everyone that is taking part in this mini symposium. We had a great response to our call, and also a special thanks to Luca Susmel, who has helped me in getting it all together. So the idea is really just to celebrate the work that has been done on the theory of critical distances, which has now risen to a really large volume. My initial intention with this talk was to review the publications in this area, but that would be just impossible because there are really thousands of them, and even in the last couple of years there are hundreds of publications. But what I'm doing in this brief talk is just concentrating on papers that have been published within the last couple of years, and in particular trying to name check people who were kind enough to be involved in this mini symposium. So I've divided the talk into four parts, which are there on the slide: materials, failure mechanisms, applications, and theoretical developments. So let's kick off. Firstly, looking at materials, I started work on the TCD in the late 1990s, and it was a big revelation to me to discover that it's not all about metals and it's not all about fatigue. I started in the same way as those early workers here, Neuber and Peterson in the 50s. They started looking at high cycle fatigue in steel and other metals as the motivation. But searching around, I discovered that there are other groups of people, other communities of researchers who are working on exactly the same idea on different materials. So here on the right you see a seminal paper by Whitney and Newsmo in 1974, where they're applying the TCD to a fiber composite material. Now there's an enormous literature in the fiber composite research community referring to this paper and using ideas which are exactly the same as the TCD, but using it for static fracture and for composites. And the same I discovered in other branches, other material areas as well. So just a couple of examples of recent work in this area and the diversity of materials involved. This, for example, is one of the many papers written in the last few years by Sergio Cicero's group, where they're using the TCD for several different materials. Here it's a short fiber composite, and I show it here really because it's what has become really a classic approach in applying a TCD analysis, where you carry out tests on notches where the length of the notch is always the same, but the root radius of the notch changes, and we get this increase in stress, or in this case the nominal stress intensity, the toughness value. We get this increase with the increase in the root radius, and you can fit a curve and find the TCD parameters. So that's just one of many examples. I think there's opportunity for doing more work on composites, especially on long fiber composites, which, though as I said there's a big literature on it, not many people are doing this kind of test. They tend to have a different approach using circular holes, and I think that there are opportunities there anyway. Turning to a slightly more unusual example, this is single crystal silicon, the work of Gallo et al. And this is possibly one of the smallest ever specimens used for a TCD analysis. They're actually loading this and testing it inside a TEM. But really the philosophy is the same. We're looking at tests on notch specimens with different root radii and consequently discovering a critical distance, which is very, very small but finite. It's of the order of 1 or 2 nanometers, but nevertheless finite. And these workers found that this is actually, incidentally, a very useful way of finding the toughness of these materials, the K1C value, which is otherwise is experimentally rather difficult. A final example, and even more strange I think, some work from my own laboratory, and Jonas Schmidt will be presenting on this, and it's one of several natural materials which we've tested, this being the wing of an insect. So I won't say any more about that as Jonas will talk about it, but there are potential biomimetic applications in understanding how these natural materials achieve their toughnesses, and the TCD analysis is a useful approach there too. So moving on then to mechanisms, again it's been a revelation to me how many different kinds of failure mechanisms can be approached using the TCD. The great majority of papers, I guess, still are about fatigue in metals, or about brittle fracture in brittle and quasi-brittle materials. But now there's quite a big literature going back maybe 20 years on fretting fatigue, and then some very recent work, again from Sergio's group, on stress corrosion cracking, for example hydrogen embrittlement. And there are also papers on dynamic failures, where the failure process is maybe not different, but the load strain rates are very high. These are kind of, I wouldn't say obvious, but it makes sense that the TCD would be extendable to any cracking type process where you have failure by a crack propagating from a stress concentration. What's perhaps more intriguing is that there are cases where it's not a cracking process, such as ductile failure, either single ductile failures or the types that are associated in very low cycle fatigue, where you have massive amounts of plastic deformation, and critical distance methods are also being used in those cases, and there's a couple of references. So it's very exciting to see what a broad range of different mechanisms can be approached. The next section is about applications, and obviously the only reason any of us are doing this is because it could be useful, because it could be applied in design processes to predict failures before they happen, and it could be applied in failure analysis situations where you have a failure and you want to understand why. And it was really gratifying for me. I think we did, maybe my group did some of the first work on trying to apply this TCD approach, and we applied it to some automotive components with Land Rover and some of the other European car companies. And it's been really encouraging for me to see and hear about how many companies are now using the TCD as a routine design approach, that it's got that level of trust and acceptance. So here on this slide I've just listed, simply from the last couple of years, papers applying this to all kinds of situations, to specific components like crankshafts, to different types of joints, which always have been problematical for predicting durability and failure, and to manufacturing operations like high strain forming, and also to try and incorporate the TCD into maintenance and inspection procedures. So I think the future is very bright there, because there are companies knocking on the door who really want to use this approach. As I've said before, the biggest kind of barrier that we found in trying to persuade companies to use the method is that it's so easy. Paradoxically, the fact that the method, like the point method, is so easy to use kind of puts designers off, and they think, well, it can't possibly work, it can't possibly be accurate because it's so easy to do, and you have to kind of push them to maybe make some predictions and see that they really are working, and then they can be brought on side. That's my experience of that anyway. A couple of specific examples that I found interesting in the recent literature. There are some very big structures now being analysed, like this bridge, and also like buildings, steel frame buildings and concrete buildings, whereby the TCD is being found useful for predicting either fatigue failures in this case, or in the effect of large loadings like earthquakes or impacts or whatever, to predict failure. Inevitably, if you have a very large structure like this, you have to have some kind of multi-scale finite element model where we have a local model that can capture the sufficient detail of the elements, and then you have a larger scale model. Now, ourselves and others have been looking at how to maybe make life easier in these situations by reducing the number of elements, by increasing the element size and still getting good predictive accuracy. And there's work going on. La Rosa, for example, is working on that. Another example of a very different type of applications, I mentioned already this large strain failure where you have a forming operation, as shown in the upper photograph there. You can get failures of the material, necking type failures, as you can see in the middle pictures. And these researchers, Martinez Palmeth, have made, again, a quite complex finite element model with large strain facilities here and plasticity. And again, they found the TCD to be a useful criterion to pull that all together. So that's just a couple of examples of these many applications that we're seeing. Finally, then, to say a little bit about the theoretical side. There are many papers in the literature and many recent papers asking questions about the theory, and this is all very good. It's great to have that kind of discussion and intellectual input. And I just mentioned a few papers here, some of which are comparing the TCD with other theories. Quite a bit of work from Berto, for example, Filippo Berto, on the strain energy density, SED theory. And quite a lot of work, Dominic Le Guillon and my friends in Italy, like Pietro Cornetti, working on the FFM, the finite fracture mechanics. See these as all related theories, all looking at some kind of non-local, some kind of description of the process zone and what's going on there, all pretty much in the realm of continuum mechanics. But just with different criteria, and it's very interesting to see how they compare. And then there's another bunch of papers there which are basically using the TCD but are making modifications to cover particular circumstances, to try and improve accuracy by using different material models or slightly different criteria, variants on the point method or line method, for example. And again, this is all very healthy and very good. What I might propose in this big discussion about theories and predictions is that perhaps the TCD can be seen as a useful standard against which to compare theories. It might not always be the best theory, but it is pretty much always a theory that can be easily implemented. If you're doing work on another theory, you can also do the TCD just to see what happens, and maybe it's better or maybe it's not. But it has that simplicity about it that maybe can be a useful standard, as I say. So finally, just to wrap that up and try and stay within my 15 minutes, I think we'd all agree that the TCD is alive and well. Over the last 20 years, it's really come of age as a practical approach and as a research tool. It's become useful as a practical approach, I think, largely because finite element modeling has developed so much that it's no longer difficult to get the necessary stress information. And I think there's naturally a lot of intellectual interest in the academic community in these different types of predictive tools. We're still not in a position to really predict the mechanism of failure, not to model the mechanism of failure at the atomic scale in detail, but we are in a position to make quite precise models within the continuum mechanics approach, and so there's a lot of nice debate going on there. It's clear that there's a strong community of researchers working on the TCD and that they are really all over the world, that there are many companies that are now using it confidently as part of the design process. But of course, there's always a lot to do. So that's why we have conferences and why we have many symposia like this. So again, a big thank you to everybody for taking the trouble to get involved in this virtual symposium, especially Luca for helping to organize it. And let's hope that before too long we'll be able to meet for real and have a real chat about this. Thank you very much.